Hello everyone, it's a pleasure to be here and an honor to present my work. I'm Nangwen from Tsinghua University. I'm going to talk about understanding and handling alert storm for online service systems. Nowadays, service quality and user experience are vital for online service systems. To ensure the service quality, engineers collect various monitoring data, including metrics, logs, and traces. Once this data violates the predefined alerting rules, for example, CPU utilization exceeds the threshold, alerts would be generated to notify on-call engineers, and then engineers would assign the alerts to responsible service teams, and service engineers would start diagnosis according to the alerts. This is the general pipeline of alert management system. This table presents an example alert with several major attributes which will be used in our approach. In practice, failures are inevitable due to the large scale and complexity of online service. However, the occurrence of a failure tends to be along with numerous alerts. This is because a service system contains many components, each of which has a huge amount of monitoring data, and different components tend to be affected by each other. We call this phenomenon alert storm. Faced with so many alerts, it's time-consuming for engineers to manually examine each alert to diagnose the failure. Therefore, to facilitate the assurance of service quality, understanding and handling alert storm are very essential. To understand the characteristics of alert storm, we present two typical alert storm cases. The first one is caused by a database server down. Due to database disconnection, the service NBank cannot receive data, which leads to a series of alerts generated by other components in NBank. Subsequently, other services calling it also generated alerts. The second case is caused by the router down, as both related application and underlying infrastructure generate alerts. To help understand alert storm, we conducted the first empirical study to investigate it based on a large amount of real-world alert data. Through this study, we obtained three key findings. First, alert storm occurs frequently, about once a week, and it takes several engineers about 1 hour on average to handle alert storm. Second, the current practice of identifying alert storm is just to set a fixed threshold which cannot fit the dynamic online environment. Third, some alerts in alert storm are irrelevant to the failure, and also many alerts relevant to the failure have certain correlation, for example, textual and topological correlation. In summary, this study further motivates the necessity of handling alert storm and provides us some guidelines. Inspired by the findings from our study, we propose the first approach to handling alert storm, which contains two components, alert storm detection and alert storm summary. Specifically, for online alert data, we formulate the alert storm detection problem as online changing point detection and adopt extremely value theory to detect alert storm adaptively and accurately. Then, if an alert storm case is discovered, the second component will be triggered to assist engineers to identify the problem. Alert storm summary includes three steps. Learning-based alert denoising, which aims to filter out irrelevant alerts to the failure. Clustering-based discrimination, which aims to divide the alerts into different groups. And representative alert selection, which aims to extract the most typical alert from each cluster to recommend to engineers. Through the above three steps, we can obtain a small set of typical alerts that are relevant to the failure and reflect the failure from diverse aspects, so that engineers can spend less time handling the alert storm instead of analyzing all the alerts. In detail, about learning-based denoising, we regard the regular alerts happening in normal states of the system as training set, and the alerts happening during the alert storm as testing set. In this way, regular alerts are normal samples, and the goal is to identify the anomalous alerts that are different from regular alerts in testing set. Thus, we extract several features from alert data and adopt isolation forests to filter out regular alerts. About the second step, clustering-based alert discrimination, we calculate the similarity from these two aspects, text and topology. The textual similarity is measured by Jirka distance, and the topological similarity can be computed by the shortest path length between two nodes on the service topological graph. Then dbScan is used to cluster alerts. Finally, we select the representative alert by choosing the centroid of each cluster. The centroid of a cluster is defined as the object which has the minimal average distance to other objects in the same cluster. About evaluation, we obtained 3-year-long real-world alert data from a large commercial bank as our dataset and collected 166 cases of alert storm as our experimental subjects from the historical failure tickets. First, we compared the EVT-based alert storm detection with traditional threshold. The results show EVT-based approach can detect alert storm more accurately compared with the traditional threshold-based method, achieving the F1 score larger than 0.9. Besides, alert storm summary approach can reduce the number of alerts that engineers need to examine by larger than 98% and perform better than existing industrial practice, manual checking and only checking high-severity alerts. Also, our alert storm summary can accurately recommend representative alerts related to the failure. Also, two major components, learning-based alert denoising and clustering-based alert discrimination, are effective and outperform other baseline methods. Furthermore, considering our alert storm summary approach is used to handle online alert storm and assist troubleshooting in practice, short response time is desired. Otherwise, service quality and user experience will be destroyed if engineers wait for a long time to get the summary results. We found that when the number of alerts in storm is not very large, for example, less than 1,000, the response time of alert storm summary is very short. As the number of alerts increases, the response time also increases, but still in an acceptable range. Finally, let me conclude my presentation. First, to better understand the alert storm, we conduct the first empirical study to investigate alert storm based on the large-scale real-world alert data. Second, we propose a novel approach to handling alert storm, which can detect the alert storm accurately and recommend a small set of typical alerts to engineers from the numerous alerts. Finally, the experimental results show that our approach is indeed effective in both alert storm detection and alert storm summary. That's all. Thank you for your attention.